All right, we've made it. We're in chapter 2. We've got a fun quote from John Dalton. These observations have tacitly led to the conclusion, which seems universally adopted, that all bodies of sensible magnitude are constituted of a vast number of extremely small particles or atoms of matter. We'll learn about atoms in this chapter. So you may know that graphite is what's in most modern pencils. If you were to cut it, a piece of graphite from the tip of the pencil into smaller and smaller pieces, how far could you go? Could you just divide it infinitely forever? The answer is no, you could not divide it infinitely forever. Eventually you would get to some smallest layer of graphite. There are actually scientists that did sort of an experiment like this where they took just like Scotch tape and graphite and they just folded it over and over and over again, and they got really thin, like they got down to like a single layer of graphite, which is kind of cool. They won an Ig Nobel Prize, I think, for that. Or maybe it was a Nobel Prize. Anyway, they won an award. Eventually, you would end up with individual carbon atoms. Carbon is what makes up graphite. The word atoms comes from Greek atomos, meaning indivisible, or not being able to be broken up any further. It's the smallest possible unit of matter. You can't divide a carbon atom into small pieces and still have carbon. It becomes something else if you were to divide it up past a carbon atom. All matter, everything that has mass and occupies space, is made up of atoms. These are the fundamental building block of everything that we can experience that's not light or the vacuum of space. Sort of relating to atoms, in the 1800s, Robert Brown looked through a microscope at some water-suspended particles that had come from pollen grains. I think if I click the link, you can click the link in your own free time. I think if I click the link, it breaks things. So I won't be clicking any links. What you would see in the video would be a lot of little tiny particles that look like they should be sitting still, and they're just like kind of randomly jumping around, like little jumping beans, sort of, but really small. No air blowing, just like you can observe this yourself potentially, just little things jumping around. They're not alive. They're not, moving themselves by some, fancy motor action. Just little particles jumping around. This is what we would call Brownian motion. He initially thought that the particles might be alive, but finally concluded that the motion must not come from the particles themselves. Einstein developed a theory in early 1900s that explained Brownian motion. So it's the result of molecular bombardments of the particles due to thermal energy of the surrounding water molecules. Basically, the idea being that these particles in the water are randomly getting hit by water molecules. And sometimes those water molecules have a lot of mass or have a lot of velocity or energy. And so they're randomly imparting a lot of energy, and that's causing the particles to shift over. And then randomly they get hit with another high energy water molecule from another side, and they shift over another direction. So what we're seeing is random fluctuations in the energy of the water that are causing the pollen or dust particles to move around. Sort of like a beach ball getting thrown into a crowd of people that want to bat around a beach ball. The beach ball isn't alive, it's randomly getting hit, sometimes with a lot of energy, sometimes not with a lot of energy, and that's causing it to fly around. So this Brownian motion, this seemingly random motion, kind of infers the existence of atoms. They were getting hit by something small that we couldn't see, but there's some motion going on that's causing the motion that we can see. Later there was some more investigation, and they confirmed it. This is a cool piece of tech, a very expensive piece of tech. So in the 1980s, some Swiss people led the development of the scanning tunneling microscope. So this is a really, really small pin, essentially. A very fancy, very expensive little tiny pin, like on a record player or something. And they take that little pin and they drop it down. They drop it ever so slowly until it gets close to the surface of some atoms. And based on the amount of electricity or potential that they feel on the tip of that pen, they collect that data, and it can tell like how far away the atoms are from the little needle, and they can move it up and down. And so you can scan the surface of things and see the atoms on them. You can also use STM to move individual atoms. So this is a picture of iron atoms on a copper surface that is the Japanese kanji for atom. So some scientists in a lab moved these iron atoms on the surface of copper to spell out this kanji. And then they took a picture of it, or rendered a picture of it. You can also, this link to A Boy and His Atom is the world's smallest movie. So they moved atoms around and made a little stop motion film of a boy and his little ball. It's like 60 seconds or something. But the frame, I think, that they used for that is like on the nanometers scale, so it's really, really small. If you wrote all the words in the books in the Library of Congress, which is apparently 35 million books, if you wrote those letters in the size of those kanji characters, then the entire Library of Congress, all the words would fit in 5 square millimeters. So like 2.5 by 2 millimeters, like a little tiny, a little pinch. So that's like the sort of scale that we're talking about with how small these atoms are. Another important definition for an atom is the smallest identifiable unit of an element. There are 118 known and named, they're all named now, elements. Many of them don't occur or don't exist, at least right now, anywhere that we know. So like on the periodic table that we've got in class, UUO, number 118 is oganesson. All of these ones that are like clear symbols, they're not filled in, those are all synthetic elements. Usually they disappear really fast. Like if you make one, it's gone in like a millionth of a second. So they're not around most of the time. That's our assumption. That's my assumption at least. So an atom is a single piece of an element, one little chunk. We've had ideas about atoms for a long time. Leucippus and Democritus from the BCs, or BCEs, were the first to propose the idea and name them atomos, that name that we saw earlier from the Greek, meaning indestructible. They reasoned that eventually, if you cut things smaller and smaller, there has to be some smallest point. You can't just keep dividing matter forever, which is a great idea, and they were right to a certain extent. They proposed that many different kinds of atoms existed, each different in shape and size, and that they moved randomly through empty space. But they didn't have any way of testing those ideas until we were thousands of years later in the future. So an English chemist, John Dalton, offered some good evidence that supported the early atomic ideas of Leucippus and Democritus. But debate continued until 1905. So we haven't been like real sure about the idea of atoms for very long in the relative scale of things. Atomic theory is the idea that all matter, everything that has mass and takes up space, is composed of atoms. It grew out of observations and laws that we're going to talk about. So these are 3 laws that we'll talk about coming up. The first, the law of conservation of mass, Antoine Lavoisier, which I think we saw early in chapter 1, proposed the law of conservation of mass. In a chemical reaction, matter is neither created nor destroyed. So Lavoisier's experiments, he had a closed container, he burned stuff in that closed container, and the stuff burned, and so it turned into new chemicals. It went through a chemical reaction. But he noticed that the mass of the container after things had all burned was the same. There wasn't matter being destroyed, and he wasn't creating new matter either. It was just changing its form. And this is generally true. When a chemical reaction occurs, the total mass of the substances doesn't change. atoms, molecules are just rearranged. So you could imagine, if we think about atoms and molecules, if we think of the atoms as being like Lego pieces, you can imagine having a nice Lego set, right? Whatever it might be. Maybe it's one of the flower sets. And one day you're taking your little orchid flower set and oops, you trip and fall, and it smashes into a bunch of different pieces, and you lost the instructions, you don't look them up, you just randomly kind of assemble them together. It's going to be a different looking flower, but probably incorporating all the same pieces. It's broken, we've put it back together, it's a different arrangement, all the pieces are still there. We haven't destroyed the pieces of our Lego set. So atoms and molecules going through chemical reactions, sort of the same idea. We're breaking one thing and then we're putting them back together in some different arrangement. So one thing that we can do with law of conservation of mass is we know if we combine things, so like if we combine solid sodium metal and chlorine gas, if we know how much of this sodium chloride we ended up with, 19.6 grams in this case, and we know how much sodium metal was used in the process, we could figure out how much chlorine gas must have been used in the process in terms of grams. The amount that we have at the start, basically just this bit, the mass of the reactants is going to be equal to the mass of the products. If they're not equal, then that means that we lost mass somewhere. So in the case of Lavoisier's burning stuff in his closed container, that only worked because he had a closed container. We weren't losing the smoke. The smoke was staying in the container. All right, when a log completely burns in a campfire, the mass of the ash, the stuff that's left over, is much less than the mass of the log. What happens to the matter that composed the log? Is it that the matter that composed the log reacts to form gases that are released into the air? B, the matter that composed the log is converted into energy? Or C, the matter that composed the log is still present in the ashes but has a much lower mass? Who's got a guess? A. It is A. The matter forms gases that are released into the air. So we haven't lost mass. Like in the grand scheme of things, we haven't lost any mass. It's just that it's gone somewhere else. The energy that we get out of the campfire is related to the bonds that form the molecules. How much energy those bonds have. We've also got the law of definite proportions, formulated by Joseph Proust, a French chemist. So the law of definite proportions states, all samples of a given compound, a mixture of two or more elements, regardless of their source or how they were prepared, have the same proportions of their constituent elements. So an example of this. Water from home, assuming that it's water, has the same mass proportions as water from Italy. So if you have water at home, you decompose it into hydrogen gas and oxygen gas, and you cleverly get the mass of those gases. If you go to Italy and you get some water and you do the same thing, it'll decompose into the same ratio of masses. So for example, the decomposition of 18 grams of water results in 16 grams of oxygen, 2 grams of hydrogen, which gives you an oxygen to hydrogen ratio of 8, or an 8-to-1 ratio. And you would expect to find the same exact ratio, mass ratio of oxygen to hydrogen for any sample of water anywhere in the world. The mass ratio of nitrogen to hydrogen in ammonia is 4.7 to 1. 4.7 grams nitrogen to 1 gram hydrogen. That's what that 4.7 to 1 means. If a sample of ammonia contains 10 grams of hydrogen, how many grams of nitrogen does it contain? We've got to guess for D. Why is it D? So we're starting with 10 grams of hydrogen. This ratio we can use as a conversion factor. So 4.7 grams nitrogen over 1 gram hydrogen. Grams hydrogen cancels. 10 times 4.7, 47 grams of nitrogen. So there's some fun stuff that we can do with the law of definite proportions. We can also check to see if two samples are the same thing. So two samples of what we assume is carbon monoxide are decomposed into their constituent elements. One sample produces 17.2 grams of oxygen and 12.9 grams of carbon. The other produces 10.5 grams of oxygen, 7.88 grams of carbon. Show that these results are consistent with the law of definite proportions. What would we expect to see if these results are consistent with the law of definite proportions? How would we show that? The same ratios. Yeah, exactly. Show they have the same ratio. It doesn't matter which one you divide by which, but it's nice to divide the bigger one by the smaller number because then we get a number above 1. So sample 1, sample 1, sample 1, sample 2. In sample 1, we had 17.2 grams of oxygen for 12.9 grams of carbon. So we can calculate what that ratio is. In sample 2, we had 10.5 grams of oxygen with 7.88 grams of carbon. We can also calculate what that ratio is. The one on the left, sample 1, 1.3 repeating oxygen to carbon. The one on the right, 10.5 divided by 7.88, 1.332, and some other stuff. Oxygen to carbon. Given that we've only got 3 sig figs, this would be 1.33 and 1.33. Those are the same. That's consistent with the law of constant or of definite proportions, because they're the same ratios. We've got one more law, the law of multiple proportions. The law of multiple proportions states when two elements, we can call them A and B, but they would take whatever their chemical symbol is. When those form two different compounds, the masses of element B that combine with 1 gram of element A can be expressed as a ratio of whole numbers. So for example, if A combines with either 1, 2, 3, or more atoms of B, then the ratios of B to A will be related by a whole number ratio. I think we have got a number example on the next slide. So carbon monoxide and carbon dioxide, they've both got just one carbon. They can both be decomposed into carbon and oxygen. The ratio of the two masses is a small whole number. So the mass of oxygen that combines with 1 gram of carbon in carbon dioxide would be 2.67 grams. So for every 1 gram of carbon, 2.67 grams of oxygen. So we're doing a ratio, and then we're doing a ratio of the ratios. So for law of definite proportions, we did a ratio of one thing, and now we're comparing two different compounds. What are those ratios? The mass of oxygen, 1 gram of carbon monoxide, is 1.33 grams, and that comes out, if we divide those, comes out to about 2. All this is really telling us is the mass of oxygen in carbon dioxide is 2 times the mass of oxygen in carbon monoxide. And since we know the chemical formulas, we can see, okay, well, we've got 2 oxygens versus 1 oxygen, so it makes sense that the mass of the oxygens would be twice as high since we've got 2 times as many. That's kind of all that we're saying with this. I don't think it's particularly profound, but it exists, so we're talking about it. Hydrogen and oxygen form both water and hydrogen peroxide. The decomposition of a sample of water forms numbers. So water is 0.12 grams hydrogen to every 1 gram of oxygen. If you decompose hydrogen peroxide, it forms this ratio. Show that these results are consistent with the law of multiple proportions. So the law of multiple proportions says that if we do the ratio of these ratios, the grams of hydrogen to grams of oxygen, 1 gram of oxygen specifically, that we should get a small whole number. So we're going to take 0.125 grams the ratio of water, the H to O ratio of water over the H to O ratio of hydrogen peroxide. Which is 0.0625 grams. That gives us a value of 2. Since we got a value of 2, that's a small whole number. That's consistent with the law of multiple proportions. Questions? All right, we will get into atomic theory next class.